Okay, so we've taken hierarchical objects which exist in the real world, and we found a way to lock them efficiently. Let's go back to this example of the system sync that I showed you earlier, where you edit, which is asynchronous system. Okay, so I can be interacting, you can be interacting, and then we can sync later. Okay, so so what happened here was that the ticket price was 23.5. And then one of us made it 24.1, the other made it 24.0. Clearly, there's a conflict. Our transaction model should detect that, and we should do something about it. Okay. And I showed you a transaction graph at that point, and I said, look, these reads and writes occurred concurrently, and I had to put one step after the other step. So I said, okay, transaction 2 did it right after this guy did a read, and transaction 1 did a write after this guy did a read. Okay, and transaction 2's write occurred after transaction 1's write. Okay? That's what I said. And now I'm going to revisit this and say, this doesn't really make sense. Okay? So what happens here? I write, I go and change a few fields, you change a few fields, and then we press synchronize, right? So when does the write occur? The read occurred when okay, and when does the read occur actually? Last time you press synchronize, you got all the data from the from the system, and then the write occurred when?
You press synchronize next time.
So somehow it takes synchronize into the picture. Okay, so each synchronize goes and reads everything that I need from the database, and each synchronize writes my stuff. Actually, in the transaction model, there is a synchronize which says write all my changes, but my read operation fetches incrementally whatever is the latest value in the system. Okay, it's because we've got a GUI here and we know what fields we need. So yes, the GUI is going to get it when it was displayed. Okay, but if we were explicitly doing, and this is here we are assuming implicit reads. If you were doing explicit reads, read this value, then the read value is the one that's the latest value that is in the common store. Okay. With implicit, exactly what you said happens, but we're going to try to be more general and allow explicit. So synchronize does the write. Okay, so clearly these guys are concurrent. There are arrows here, but the direction of the arrow we don't know. Whether it's one before the other, or the other way around. So we've got to really do something different for our rules in our rules about concurrency control. Okay, we can't look for cycles because these arrows are no longer directed. Okay, what a transaction writes is not what another transaction reads unless that transaction has done a sync already. Okay, and so you have to model sync somehow. So what does timeline mean here? Really, it doesn't mean anything unless we look at the sync operations. And so sync should be a first-class operation known to the transaction system, and it should do its. And so I could have modeled it this way also. And the real point here is that if you have two concurrent transactions, there is no leakage of information among the transactions. Okay, it's not as if my incremental writes are read by you. Okay, when I commit everything, then it goes to the shared object, and you're reading the shared object, not what I did incrementally. Okay, so you're reading the full committed value. Okay, so there's no incremental sharing. So this is much harder to model, and the way they do this is they talk about not just operations. They talk, and when I say they, a guy from CMU called Kung actually came up with this model. This is the model for optimistic transactions, and he divides a transaction into 3 phases. Okay, it's not that you do transactions and you say just commit. You have a read phase. Okay, a read phase, you go and read the operations in the shared object, and you can do writes, so it's kind of a misnomer, but the writes don't go to the shared object. They're done in a local cache. Okay, so it's called a read phase from the point of view of the shared object. Okay, Then when you're ready to go and commit, you're not just allowed to commit as in the incremental sharing model. Okay, in that model, when we do locking, we can do incremental sharing with locking or without locking. Without locking is a complicated model. Again, I think there was a guy called Reed from MIT who did that, and it's called a multi-version model. Okay, I'll go and put notes on the web that describe that model also. Okay, it's not the most practical model. I'm discussing more the practical models in this class. Okay, so the fact that you got a lock was fine. You know, that this was a pessimistic model. You got, you know, you assumed that you would have concurrency conflicts. So on each operation, we check whether you have the lock or not. Here, you just do your operations without worrying about locks. Okay, you can in fact be disconnected completely. So then, when you're ready to commit, you have to first go through a validation phase, saying, "Hey, transaction system, can I go and write all my stuff to you?" And if the answer is yes, you write. If the answer is no, the transaction is aborted. Okay? So this is the optimistic approach. It assumes that conflicts won't occur. Okay? You won't have many aborts. And there's a lot of research that's been done in coming up with workloads and seeing which one is going to be more efficient than the other, depending on the workload. But this one just assumes that the workload is such that the transaction load is such that there won't be conflicts. Okay? And at validation time, your transaction is given an ID. Okay, it's given a sequence number. Okay, so let's say this one is given the sequence number of 1. Okay, and what the system tries to do is validate that all transactions that have higher timestamp than you don't interfere with you. Okay, so it tries to say that, look, I will serialize transactions in the order in which they came to the validation phase, and if I can find that particular order equal to I can find their action. So that is the serial order I'll assume, but I'm trying to see whether the actions are consistent. Okay, so in the previous approach, we said, did these conflicting operations were these conflicting operations equivalent to some serial order, and that order has to be figured out. Here we say we're going to fix the serial order in terms of the validation phase, and now the question is, did your actions conform to this particular order? If not, we'll abort, and you can try again later. Okay, so that's the whole idea. So this is validated. Now it goes to validation phase, and we can see from this particular example that there is an interference. So this transaction, one transaction will write, and the other transaction will abort. Okay, and why is there an interference here? Why is this not equal to T1, T2 serially?
Because R2 reads the price before R1 writes it?
Yeah, R2 reads the price before R1 writes it. And if it was to be serialized in the T1, T2 order, R2 should have come afterwards. Okay, and we're not even going to try to see whether it's T2, T1. Okay, it's not T2, T1 either. But we always do it in the T1, T2 order. Okay? So let's come up with some rules to see when we know that in this case it failed. So let's come up with general rules for validation. Okay? And before I go into that, optimistic concurrency control divides a transaction into a read phase, validation phase, and a writing phase. Read phase, transaction reads shared items, doesn't write to the shared object, writes to the local buffer, but not. And no checking is done, okay? And validation phase, the timestamps are assigned and checking is done. Write phase follows a successful check, and if successful check doesn't occur, then the transaction aborts. Okay. So now, by the way, if T1 and T2 interfere, and T1 came before T2, which one should you abort?
T2.
T2, that's the natural thing, right? T1 has already come earlier, and T2 came later. T1 is already written. Okay, so you'll have to go and undo all those changes. Whereas if you abort T2, we just don't have to make those changes. But Logically, you can do either. Okay? If T1 just corrected a typo and T2 rewrote the whole paper, then maybe T1 should be aborted. Okay? So depending on the mix of transactions, you can come up with one or the other. So let's assume that T1 is the one that's validated, has already handwritten. Now at this point, so this is what happened. T1 went and read and wrote to O1, and after T1 wrote this value, T2 went and read these values. Okay, and then it went to its validation phase, and the validation would say that's just fine. Okay, independent sets of dependent sets of values, but my reads occurred after your write, so that's fine. Okay, so transaction Ti is validated with respect to transaction Tj for all j greater than I if Ti finishes the write phase before Ti begins its read phase. Okay, you can say the other way around also, that Tj is validated with respect to Ti if its reads where I is less than j, if its reads occurred after Ti wrote its stuff. Okay. Any other conditions you can give for validation? This is sort of the trivial condition. In this case, the set of items overlapped, right? If the set of items, so this is equivalent on locks on same object access. Should this be validated?
Probably.
Because
they're working on different objects.
Different objects. Okay. So this is again a simple rule. Ti does not read or write any items written by Tj. Okay. So actually, I could have had this be R1 O3, and or this could have been R1. The whole point is that it should. There's just no interference. Right? It doesn't matter what this transaction read. It matters what this transaction wrote. That's what I'm trying to say. Okay, because that's when there's leakage of there's interference. Okay, so this transaction could have read O3, and that's okay, even though this guy reads O3 because he didn't write to O3. Okay. So equivalent of different locks on different objects. Okay, now any condition left? So we've looked at the condition where your actions are following the actions of the other one. We've on the same object. We looked at the condition when you aren't reading some object that the other transaction is writing. Look at this schedule. You are so in this case, you are writing something that the other transaction wrote. Okay, but your write follows this guy's write, and your reads all occurred on operations on objects that this guy didn't write. Is this covered by the previous case? I think the previous case said that, I don't want to go back, that you write on disjoint sets. Here you are writing on the same sets, okay? But your write just happened to occur after that guy's write, okay? So this is the most interesting rule, actually. Transaction Ti is valid with respect to transaction Tj if Tj does not read any of the elements written by Ti, and Ti finishes its write phase before transaction Tj begins its write phase. Okay? So there were three rules, and again, I don't want to go back to the previous one, but I think in the previous one we assumed that the writes were on disjoint elements, and here the writes can occur on overlapping elements. Okay? It's just that your read should occur be on disjoint elements, and your writes, as long as they follow, that's okay. Yeah.
So the transactions are valid if any of these three conditions are met?
Yes.
Okay.
The transactions are valid if any of these three conditions are met.
So we're assuming in all these cases that there's no conditionals or anything happening within the transactions.
No, we assume the conditionals are happening.
So I guess the one before this one where we talked about reading one value and then writing another.
Okay. So during the locking time, somebody writes and I read their value. That's incremental sharing. No incremental sharing here.
No, I'm saying just thinking of transactions happening in isolation. Like we're talking about as long as you're writing to different areas in the previous case, everything's okay.
Yes.
But
also, as long as you're not reading what somebody else wrote.
okay.
As long as you're writing to different areas,
Okay.
that's fine. But you're not reading what somebody else wrote. That's important. And that's why we have this thing here. That yes, you can read concurrently, as long as what you read is not what the other guy wrote. And in this case, and this is the second case, I don't know if I phrased it right or not, but the second case was really saying that your writes occur on different operations. Okay? Here you're saying, yeah, your writes can occur on the same on the same operation, but then if that happens, the write should follow the previous guy's writes. Okay? As it's going to allow fewer schedules than locking. Because and I think I've got something. So I thought I removed this. Just ignore this one. I think I phrased it better, or unless I didn't get my latest updates here. So in this case, you're going to abort, right? Because you read something, maybe my changes didn't go through. This is the same as before, right?
Yeah.
And I meant this to be O1, okay? So in this case, you are going to abort. But in the locking case, this would have been allowed, okay? Because you're allowed to incrementally read what somebody else wrote. But because in that case there's incremental sharing, this would be allowed. In this case, the writes haven't occurred. So this schedule is not allowed. That's what I'm trying to say, that in the optimistic case, and again, I'll try to remember this is O1. Okay? So RW transaction dependency, which is same as WR dependencies. There's no arrow here. Okay? They cause aborts, and this is where you have this kind of dependency here. And that's why. So you don't have to look for cycles. Just the presence, just the fact that I read something you wrote is enough to cause one of my transaction to abort. Okay? Whereas in the locking case, we had to go and see that, I depend on you, you depend on me, so now we have a cycle and it's not allowed. Okay? Because no incremental sharing. Okay, so did I answer your question, John? Transactions are not easy to get your head around. Okay, there's a lot of concurrency is one of the most interesting and intriguing ideas, the guys here who do real-time computing have also got to do with concurrency, deal with concurrency a lot, and often the real-time computing guys don't really get don't look into transactions very deeply. But there's actually, having heard enough of Jim Anderson's talks, there's something called serializability here, right? There's something called linearizability in real-time systems. and they're very similar to each other. Okay, and the points are very subtle. At one time, I thought I understood those, but I've forgotten what. I haven't heard one of Jim's talks recently, so it's not in my cache. Okay. So locking has the advantage that you have incremental sharing, right? You can allow more schedules. And can you think of a disadvantage of that? We're going to compare pessimistic and optimistic in great depth later, but just the incremental sharing part. The good thing is that I can allow certain kinds of interleavings. The fact that I've leaked some information to you, could that cause problems later? And I leaked this information to you before I commit it. What if I decide, my if statements that say, I really didn't like this. I'm going to abort my transaction. Right? What does that mean? We saw that last time. I should abort this because it has gone and read values from this transaction, and we have to pretend this transaction never occurred. And its values could have been read by. Okay. So we have the problem of cascaded aborts that I referred to last time. So incremental sharing causes these problems. And for this reason, often transactions just want to keep the locks till the end so that you don't leak information. Okay, so it's not such a, again, depends on the workload. Okay, and there's a lot of papers being written on different kinds of workloads. Okay. And like I said, in locking systems, problem is avoided by keeping write lock until end of transaction. Okay, so there is these three kinds of validation. Early, okay, pessimistic transactions that you're validating quickly as you access, you validate. Okay, late when you commit, and then there's the merging alternative. Okay, and in pessimistic, you prevent conflicting operations before it's executed, before they are executed. Implies locks. No, it doesn't really imply locks. Locks support it, and possibly a remote. Okay, so possibly remote checking means, of course, you might have to go to, as in your assignment, you might have to go to some faraway site to figure out whether you have a lock or not, which means you have to have a connection to that site also. Okay. And optimistic, you abort conflicting operation after it executes, and involves replication, right? Your cache is a replica of the shared object. Checkpointing, where your actions are copied now then from your local database into the remote database, and you keep a log of these operations that can be replayed in the shared object. And we assume that the log can be just we assume that if there's reads and writes, you can just erase the values. But what if there was some kind of side effect operation? Okay, I sent a mail, I printed a check. You need some kind of compensating transaction that goes and says, sorry, bank, please go and invalidate the check. Okay, I don't know how you undo a printing job, but you just make it illegal to read the document. So you just need to take some actions, some compensating transactions you have to execute to go and undo your effects. Okay, you can't just erase values sometimes. Okay, so under what conditions might you use pessimistic, optimistic? These are the features. Assume we can implement them. Or what are the pros and cons in general? Let's look at performance. Which is going to perform better?
Assuming nothing goes wrong.
Assuming that, that's the optimist. Okay, so assuming the assumptions of optimistic transactions, optimistic should win. Why?
Because we don't have to do any logging, we don't have to do any waiting.
Yeah. And no checking. Right? And
There is something interactive, then we should probably go with pessimistic because we can't backroll.
very good. Okay, if there's something interactive, we should probably go with pessimistic because we can't undo an interactive transaction. In that case, your locking semantic use UI better be pretty good, right? Because it's a pain to use. Or you use merging. Okay. So per operation checking and communication overhead, no. You can compress also. You know what? You may go and take a sequence of actions that are a bunch of writes and replace them with one write. Okay. If I'm writing to A, B, C, and D, A, B, and C, I might be able to do it more efficiently by doing a block write to the whole object, for instance. Okay. So there's compression possible. There's no compression possible in the incremental case. Prevents inconsistency possibly resulting in lost work. Okay. So when inconsistency happens, okay, you lose work. Tight coupling of incremental results. Okay, I see immediately what you're doing. Okay, which may or may not be good. You know, we were talking of pair programming and how you don't want to be bothered by other people's updates, perhaps, and want to work in isolation. This allows more parallel development. You know, let me just try my idea out without seeing your incremental changes, and then we'll see later whether my ideas and your ideas compose. Okay, and this is the big deal that you know, you assume you know, this won't work if you're disconnected, unless before connection I just lock everything, okay, and don't let you work at all. So I go off to the beach, I lock everything, and nobody in the office can work because I've got it locked, right? Whereas you can work, you can function, and that's where merging comes in. Allows operation to execute without local checks, and if I insert character A at position 1, you insert character 2, B at position 2, you know, they can conflict. My B might not be added if you had added the A. Okay, but we'll just say, we forget, we only look at write actions. We assume that nobody ever reads anything. So yes, my insertion didn't depend on your insertion, and we can just go and modify, as we'll see in, we can make this equal to either this or this. So this is not serializable because you ignore reads, and we essentially, like I said, define a new transaction that replaces the previous transactions. Okay, and this is often very application specific. Okay, let's see if we can do at least one more idea before we leave. So we looked at hierarchical shared objects. Okay, let's go back to hierarchical shared objects. Can you have hierarchical transactions also? And what would that mean? So it's the operations that are hierarchical. It's not the data. Okay, so somehow one thread spawns another two threads, which spawn more threads, and they're all connected in a hierarchy. And what does that mean? So let's say we have this paper, and our job is to fix the paper before deadline of 5 p.m. today, right? So I might have two transactions that are sub-transactions of this. One guy is fixing the typos. The other one is moving figures around, okay? And this is, you know, this is not a concocted example. This has happened many times to me with my students. Okay, this is what we're doing just before the deadline. And the fixed typos transaction, you know, could involve read abstract, then write abstract, read introduction, write introduction, and move figures could be, you know, okay, let's move this figure from this introduction part of the introduction to this part of the introduction, okay? And then, you know, you want to check in fixed length, okay? This again happens so many times, okay? I can't tell you how many times I have to look for synonyms so that I can save 2 characters and make my line not wrap around and go to 10.1 pages long, okay? And then you submit paper, right? So does that make sense? Sub-transactions, this is a transaction, these are child transactions, and these two operations belong to the top transaction. Okay, so each transaction can have operations. It's a thread, it does some actions, okay? And this idea, I believe, came from Barbara Liskov at MIT. Barbara Liskov, anybody heard of Barbara Liskov? She's also a Turing Award winner like Fred Brooks. She's visited our department a few times. When I was at Purdue, she visited us there too. And she came up with a programming language to allow this stuff to happen, language called Argus, which is the first research paper I ever read in my life. And so I think all the transaction model spawned from that language construct. Okay, I believe a guy called Elliot Moss was one of her students who came up with the whole model after that. Okay, so this is the action. It spawns two sub-actions, and then also in the background it goes and does its code. Okay, think of that as a programming language construct. Now, what does it really mean? And to understand that, so the actions are hierarchical rather than the data. So to understand what this means, let's go and contrast it with just doing everything in one transaction. Read abstract, write introduction, check and fix length, submit paper. What's the difference between this and what this could be? We don't know what this could be. We know it's not this. So why would we not want this? Let's put it this way. And that'll motivate why we have this. I kept saying my student and I always put two people there.
Multitasking?
So this is all I do it. Operations of a transaction have to happen serially. My student just watches over me and tells me, okay, and that's not a bad idea, by the way. Okay, but this is pair programming. They're just watching me while I do all the actions. Okay, and it's going to be 5:01 when we submit the paper, and there goes a chance. Okay, so this sub-transaction, that means sub-transactions of a transaction, unlike the sub-operations of a transaction, can execute in parallel. Okay, that's kind of what I show in a timeline here. Okay, so we have some idea of how this is different from this. So then, how is it different from this picture? 3 independent transactions occurring in parallel. I have to put another co-author now in, my student, me, and another student, okay?
The fixed paper should, this action should happen after you
the fixed paper operation should occur after these guys, okay? So somehow there's knowledge that these operations, these two operations are different from this. And if the fixed paper doesn't happen, what can there be an issue if the fixed paper operation never occurred at all? You're not going to be consistent. You're going to go over over the length. So what are the 4 properties of transactions we saw? Atomicity, consistency, isolation, durability. Should these 2 transactions be isolated from each other? They're executing concurrently. They better not step on each other's toes. Should the actions of each transaction be executed atomically? Should they be allowed to abort? Saying, I fixed this, moved this figure, I moved this figure, and this happens in Word a lot. Okay? I can't, the paper's in a mess right now. Okay? And I do just abort that. So they should be, they are units of atomicity. Is each of these subtransactions a unit of consistency? Do they leave the shared object in a consistent state? Is the paper within 10 pages? That's what we just saw. It may not be. So these subtransactions have no responsibility to leave the shared object in a consistent state. That's Okay, and since they're not in consistent state, there's no need to make it durable. Okay, so that is the key here. That subtransactions do not guarantee consistency, and the results are not durable. Okay, they are atomic and serializable with respect to each other. Now, the parent operations can occur concurrently or may not occur concurrently. Okay, there are two different models, and in this example, we want the parent's actions to basically follow the child's actions. Okay, but if they occur concurrently, then the parent's actions are not serializable with respect to the children's actions. Okay. So what happens really is that the parent, now there are two models here. There's the optimistic model and the pessimistic locking model. In locking model, the parent gets the locks from the shared object in some mode. The children's transactions then get the locks from the parent in a weaker mode, but not in a stronger mode. Okay. Similarly, in the optimistic model, the parent goes and reads values in, and the children then goes and reads from the cache the parent got, and the children go and write to the right set of the parent, which then goes and writes ultimately to the database. Okay, so it's like there are multiple levels of the shared object. There are multiple versions of the object, and you're writing to your parent's version and reading from the parent's version, and that's the intuition here. Okay, so top level transaction gets a shared object locks. So concurrency of parent may wait until subtransaction finishes. Okay, and in Mesa there was a function called join in a thread. You can join the subthreads, and Mesa is a language from Xerox, and Java basically has exactly the same name, and you can say join a thread, which means you're waiting for that thread to finish. Okay, and that's what we need in this example. You want to wait, but they may execute in parallel. So subtransaction not serializable with respect to parent. That means they can both execute on the same. They don't have to. The child doesn't have to. Once well, the locking semantics are such that both actions are allowed, and when the child wants to do an operation, it can ignore the fact that the parent wants the lock. Okay, so it can just do the operation. The child wins, and the parent, if the child has locked something that it has locked from the shared object, the parent has to wait. Okay, the idea is that the child has to go concurrently, and the parent can all. So one of them has to win, and the child wins. Okay, let's look at this here. Abort semantics. So the child T12 is trying to move the figures around, and the figures are totally messed up. Okay, and it aborts. Should the parent transaction abort at this point? Yes. When the child commits, does that write stuff onto the shared object? We just saw no. For the same reason, the abort of the child doesn't have to abort the parent. In fact, the parent can try another transaction. Okay? And then commit to the shared object. Okay, so that's another reason why they wanted nested transactions. Okay, child aborts do not abort parent transactions, but parent can try alternative transactions.
Okay. So, but they have to have alternative transactions.
Yeah. Otherwise, they can abort. They can always abort and say, "Oh, my child couldn't do it. I give up too." Yeah. But the buck stops at the parent, right? It's the parent's fault then. And again, this is complicated stuff, but I think it's very practical, especially in the collaborative domain, okay? Because you tend to have these sub-transactions, okay, like I said with this paper example. Okay, so I kept referring to nested transactions in my examples, and I wasn't going to teach you guys this stuff, and then I said, might as well. Okay, so this is a summary. Like top level, atomic and isolated with respect to siblings, not unit of consistency or durability. Actions do not conflict the parents' transactions. What it really says is that, since we just use priority to determine who gets to go, and we don't have to worry about dependencies and so forth because the child's actions don't have to be serializable with respect to the parents. Okay. Okay, we have 10 more minutes, and let's come up with what I think is the most interesting stuff in transaction systems. Okay. So, before I did nested transactions, whatever I described to you was invented by database people. Okay. And if you talk to a database person, that's what they probably know. Nested transactions, they got invented by a programming language person. Okay, you guys, Barbara Liskov, let me tell you, this is so in Java there are iterators, and that didn't get invented till Java 1 point something, 1 point greater than 1. Okay, iterators were invented by Barbara Liskov in 1970 something. Okay, so the same person who did sub-transactions did iterators, clue iterators. There was a language called clue, and there was something called clue iterators. Okay, so that stuff came from programming language stuff. So now I'm going to talk about something that came from operating system people. Okay, and this to me really goes and helps you understand what transactions are all about. Okay, so let's take our example that we saw earlier and see how we can model this using our transaction model that we've understood so far. Okay, so I go and say, please, show me, tell me whether a README file exists in this particular project or not. If so, it'll show me that element. So basically, I'm doing a member operation on a set. Okay, and if it does exist, I will go and edit it. Okay, this goes and says, is SRC a member of the project? If it's not, let me go and create that member. Okay, so I'm doing essentially set operations. And we would model this as read project, write project. Okay, and based on that, we have a conflict. And yet we know that these operations don't really conflict. Right? We know that because we know these are sets. Right? When you're reading the project, you're not reading every element, you're just checking if a particular element exists or not. And here you're checking if this element exists or not. Okay? And when you write to that particular element, this read operation is not affected. We know that. And yet, if we go and take the transaction system invented by database people, we'll have to go and say no. So what we have to do now is look at the database as not a database, but an object in programming language terms. An object as an abstract data type with some operations. Okay? These operations and the transaction system can do different things based on how well it understands that object. If it has a lot of information about sets, it could do a different job than if it has very broad information. Okay? So set operations are serializable, read-write operations are serializable. So we're going to talk about type-specific serializability, that how when we define a new type, we might want to define a new transaction system. Okay? And to what we might have to define a new transaction system, or we might have to go and give the transaction system some information it understands. Okay? So modeling as read and make leads to directory independent non-serializable case. This is just saying in text. So what a transaction system could do is not be tied to read and write operations. Okay? It could be tied to some X and Y operations, where X and Y are anything. Okay? And in that case, it needs to know about dependencies. And we'll say that it has a dxy dependency. A transaction T1 has a dxy dependency to T2 if transaction 1 performed operation X before transaction 2 did Y. And that X and Y could be bound to different operations. They could be bound to read-write, set, queue, and other operations. Okay? So that's the theory here, that we'll create this transaction graph and we'll create these dependencies. And then the question is, what kind of dependencies could we know about given a new type? that type could be a total black box to us with a bunch of methods. And we don't know what get price is, what set price is. We just know it's a method that can change the state or read the state. Okay? In that case, there's only one kind of dependency that the transaction system can know about. Some operation got performed by T1 before some operation got performed by T2. Okay? In that case, T1, D, any, T2. Okay? So if we have get price, set price, and get price here, the dependency between these two operations is, so, and serializability would mean there are no cycles in the D, any relationship. Okay? So we have D, any here, D, any here. We don't know this is a read. We don't know this is a write. We don't know that reads are commute. We assume any any pair of operations don't commute. Okay? So given this schedule, if all we know is that the operation is some operation that could do read or write, we will disallow this. Okay? So this at least shows you that based on what knowledge you have of the ADT, you may make some transactions serializable, schedule serializable, some not serializable. Right? If there's a cycle here. What if you have this? Is this serializable? There's no cycle. It's kind of silly, right? There's only one operation here. But let's say this was get price, set price, and then there was some other operation that's on a separate object. Okay? This is serializable. It's not as if every schedule is not serializable. Okay? But this one is not to be allowed if you want to prevent cascaded aborts. Okay? If you want to prevent those, then you don't allow this dependency to be formed. Because this could have been a write, and this could have been a read, in which case we don't allow this. Okay? So a transaction system has to do two things. It has to say, is this set of is this schedule serializable? And is this schedule cascade free? Okay? Cascade free is a stronger condition than serializable. Okay? And serializable, you look for cycles. Cascade free, you look for certain kind of dependencies. Okay? Okay. So not allowed if cascaded aborts are to be avoided. Now, we're going to make this less black. We're going to make this gray. And tell the transaction system, get price maps to read. Set price maps to write. So the transaction system now works in reads and writes. It doesn't know about get and set, but it just knows the mapping between the actual operations and the operations it understands. Okay? Now, there are four kinds of dependencies. There's read-read, read-write, write-read, write-write. That can form, right? Now, X and Y come from the set read and write, so there are four combinations. Right? And for serializability, what we have done so far is said, this commute, I mean, I've been saying this implicitly so far, I'm saying it explicitly. This dependency commutes, these two operations commute, so we will look for no cycles in the relationship D, where D is D2 union D3 union D4. D1 doesn't count. Okay? So we never drew arrows between two get prices, and this is DRR, we are drawing an arrow now, but we're going to ignore it. And this arrow we don't ignore, and this transaction is allowed because this dependency doesn't matter. Right? So, serializable. This arrow doesn't count in our thing. Okay. To prevent cascaded aborts, we don't allow this dependency to form. The transaction 1 writes, and later transaction 2 reads this value. It's okay for this dependency to be formed, where transaction 1 reads and the other transaction writes. But this dependency cannot be formed. Okay? So this is fine. This is cascade free. Okay, so we've seen very concretely that by knowing more about the ADT, we can do better. And what we'll do next time is see how we can build a transaction system that is better than read-write transaction system that knows type-specific information. And we'll see that read-write information will be far more conservative, like the set example we saw. Okay, we'll take a queue because this came from OS guys. They gave the queue example. And we'll see that how modeling the queue as just read-write, operations read-write are going to cause problems. Okay? So that's what we'll do next. Okay. So the motivation for what I'm going to do next is a queue. Okay, or basically, in more generally, an abstract data type. And even more generally, trying to really understand what these graphs, transaction graphs mean, and what serializability, what ensuring serializability and ensuring a lack of cascaded aborts really means in a more fundamental way. Okay, so so when we draw transaction graphs, and these directed edges make sense only when you're doing incremental sharing. Okay, when you're doing optimistic transactions where you really don't read what other person's writing, the arrows mean nothing. Okay, so this is really when you're doing incremental sharing, and there's many ways to do incremental sharing. Locks is one of them. Locks is a practical way of doing it. There's something called multi-version timestamping, which is a brilliant idea. Basically, for every write, you create a new version of the object. Okay, but it's it's a lot of versions. So for us, incremental sharing and locking will be pretty much synonymous. Okay, so these are the two questions we're trying to answer. So we drew these transaction graphs, and then there are these arrows. And what do these arrows really mean? And we said there's a dependency. Okay, and there's a dependency that matters. Okay, so we have to figure out what dependency really means and what a dependency that matters really means. And dxy means that transaction 1 did operation X before transaction 2 did operation Y. Okay? So in general, an abstract data type might have multiple kinds of operations. Okay? Read and write are operations that something like a bean would support. Okay? And the idea is to go and so given an abstract data type, okay, if we know nothing about that type, okay, that's what often we consider as an abstract data type. It's just a black box. Okay, so if it's a black box, we don't know what the word get price means or set price means. We're using no conventions. So there is only one kind of dependency. Transaction 1 did some operation before transaction 2. We can't classify the operations in any meaningful way. Okay? We don't know how to understand them. Okay? So when we draw these graphs, we'll draw, depending on these, on the timing of the operations, we'll just put these any edges between operations occurring at different times among concurrent transactions. Okay? And we very quickly get into cycles. Okay? Because our conservative approach would be to assume that every operation conflicts with every other operation, and so we have to we get into cycles when semantically we know we shouldn't get into a cycle. We know that two get prices. Now we really don't know what get price does, right? The get price method could do anything. It could set the price for all we know. Okay, but we are going to assume that get price is going to only read the value. So in which case. And if we assume that using our semantics, not our transaction system doesn't know this, we know that the two reads don't interfere with each other, and that information is not captured. Okay? So it's not serializable. So and that's for serializability. For cascaded aborts is a stronger condition. Preventing cascaded aborts is a stronger condition. It says, yes. With serializability, we know these concurrent transactions aren't serializable, but one transaction may be leaking information to another transaction through incremental. One transaction might write something, the other transaction reads. So the first transaction aborts, we have to go and abort the other transaction also, the following transactions also. So what we do is we say there is no, among concurrent transactions, we basically allow no dependency. Okay, so we are really serializing access. Okay, so this is, if you're going to prevent cascaded aborts, we'll serialize access. So that's not very concurrent. Okay, so moral is we need more semantics, and we know in this case this guy did a get and this guy did a set. So the read operation occurred before the write operation, not vice versa. So we know no information got leaked, but that information is not being captured in a transaction system, by a transaction. So now what we do is we expect an ADT definer to go and label methods as read methods and write methods. Okay? And if we do that, we can use read-write semantics. And when we have read-write operations, we have 4 combinations of X and Y. Okay? So there are 4 possible D relationships. Okay? But we know that R and R commute. So this is not an interesting operation from the point of view of serializability. Okay, so we look for cycles in the D relationship where D is a union of all dependencies except D1. Okay, so now this is DRR. This is not not member of the D set. This is member of the D set. So only one of these dependencies really matters. So this is a serializable schedule. Okay, we saw that last time. Okay. So moral is more information. Our serializability semantics can allow, our serializability enforcer can allow more concurrency. And now for cascaded aborts, we have to look for DWR relationships, and we know this is DRW, so we allow this schedule, whereas if you're being very conservative and not allowing cascaded aborts, we won't have sorry, if you're being conservative and not allowing it, this would work. If we were using DNENE, we wouldn't have allowed this. Okay. Okay. So that's where we left last time, and I very quickly introduced to you this slide, and I said, okay, let's go to. So in the previous slide, what we did was we took a transaction system that understands read and write operations, mapped our ADT operations to read and write, and used that transaction system. We didn't have to write our own transaction system. Now I'm going to motivate writing our own transaction system. Okay? For a specialized object, we might want to do specialized concurrency control. Not based on read and write operations, but based on very specific operations provided by that object. Okay? And Q is a very popular data type, especially if you're an operating system person. So the research I'm going to talk about came from some OS people at CMU. I think it was Schwartz Inspector, but I forget. We have 2 operations, QDelete and QEnter. QEnter takes as an argument an element of some type, and QDelete returns an element of that type. Okay. So I'm going to abbreviate these operations as following. If the Q operation enqueues X, then I'm going to call it EX. If the delete operation doesn't really take an argument, okay? But if the delete operation returns X, I'm going to say DX. Okay? So again, X is a return value. It's not an input value. Okay? Okay. And we're going to assume, so what are X? It's not the actual element that you're entering. Okay? It's an ID of the element. So each element has a unique ID, so we can distinguish one element from another element. Okay? In a queue, you could have two elements that are both have the value A, okay, but they will have different IDs. Okay? Just like hash code or system hash code in Java. So why might Q semantics help? If we were not to model Q directly in terms of QDelete and QEnter, then we have to map each of these 2 operations to read-write operations. Okay? So what is QDelete? It's a read followed by a write. It's a read because you return a value. It's a write because at the end of the operation, the Q has changed. Okay? QEnter, is just a write. Now, QEnter to do its job might have to go through a linked list and read the elements till it reaches the point at which it should enter the new value, but information about the elements is not leaked back to the transaction that executed QEnter. So logically, there is no information leaked out, so there is no read happening. Okay? So let's take two transactions. The first transaction adds an element with ID A. The second transaction deletes an element that's different from A. I got ID C. And transaction 1 enters an object with ID B. Okay. Now, is that serializable based on our Q semantics? That means we should be able to execute either T1 before T2 or T2 before T1. And this particular operation would return the same value whether it's executed before T1 or after T1. Okay, because C is ahead of A and B, so no matter in which order you execute the operations, it'll return C. Okay, so these transactions based on Q semantics are serializable, but if we were to model them using read and write, we run into problems. Okay, transaction 1 is doing an NQ. NQ is a write. Okay, transaction 2 is doing a DQ. DQ is a read followed by a write. So we have a write read and a write write dependency. Okay, the writes come from the QEnter, and these reads and writes come from QDelete. And then we have a DRW dependency from here to here. Okay, but that doesn't count. And we have a DWW dependency because this particular transaction did a write, and this transaction did also a write. Okay, this read, it doesn't matter. So we have a cycle, and the transaction is not allowed, the schedule is not allowed, but based on Q semantics, we can serialize either T1, T2 or T2, T1. Okay? So not serializable, even though two transactions working at different ends of the queue. Not serializable under read-write semantics. Okay? So the other is cascaded aborts. We want to avoid those. And we have a DWR dependency between these two transactions. So it seems as if what this particular transaction wrote was read by this, but that's in fact not true because they were working at different ends. So this is under read-write semantics, this is serializable, but it's not allowed if cascaded aborts are to be avoided because of this DWR dependency, which is really a false dependency. If we had Q semantics, we've already seen. Now, what if I go and change that to NQC? Is this serializable based on our high-level semantics? We know according to read-write semantics, it's not going to be serializable. According to the Q semantics, it's not serializable. Why not? Okay, so either both A and B should occur before C or after C. We can't have them interspersed. Right? So we have a dependency on this guy. Okay. What about this? Is this serializable? Transaction 1 DQ'd A. Transaction 2 DQ'd C. Transaction 1 DQ'd B. If transaction 1, T2 executed before T1, what would transaction 2 DQ? If T2 executed before T1, what? It would DQ A. Okay, and if executed after T1, it would DQ B. Okay, so this is not serializable. Okay, so we have to now come up with some semantics that allow this schedule, but don't allow the other two schedules. Okay, so you said we're going to check if Q is empty. So how do we model that? So what kind of lock do we want to get? What kind of locks do we want to get now? We got read and write locks when we had read-write operations. Okay. Now what kind of locks should we get? We could get NQ and DQ locks, but that's not enough. Because we saw, so do the NQ and the DQ locks conflict? Yes in some cases, no in the other cases.
There shows a log to know that whether the Q is empty or not empty. If the Q is not empty, then the DQ can operation can happen. Even in the Q.
Okay. So you're saying somehow the lock should reflect emptiness, right?
Yeah.
What if the Q has one element in it? Okay. And then transaction 2 DQs 2 elements. So when transaction 1 got the lock, it got the lock because it was not empty, and later it became empty.
Yeah.
And how do we reflect that? Lock on the number of elements, but that number can keep varying during the transaction.
Yeah.
Yeah.
Could we acquire a lock for each element we're going to DQ?
Could we acquire a lock for each element we DQ? We go and say, if I do the operation right now, I would get this element. So I'm getting an NQ. So basically, the element DQ'd by T2 is not an element queued by T1, right? That's the whole key. So when we go and get our locks, we are going to go and say, we are going to specify in the lock the element. Okay? And then we can go and write a compatibility matrix based on that element that somebody has locked. Okay, so now when somebody goes and tries to NQ, they say, okay, I'm NQing this particular element. So I'm getting a lock, NQ lock on this element. And later when somebody tries to DQ, they say, okay, if I DQ, I'm going to get this element. Can I go and check whether my DQ, this element lock, conflicts with the NQ, that element lock? Okay? And that's how we're going to build a lock compatibility matrix. Okay, so that will allow us to allow the queue to get full or empty during the transaction, and the number of elements to vary during the transaction. Okay? So we're going to have now the following kind of dependencies. Okay, so we're going to get those kind of locks, and we're going to basically see whether the elements in two competing concurrent operations are the same or different. Okay, so when we're going to write our write our lock compatibility matrix and write our dependency relationships, we won't tie them to specific locks, but to whether specific elements, but whether elements in two different operations are the same or different. Okay, so D E E E E prime means that transaction 1 NQ'd element E, okay, small e, and transaction 2 NQ'd another element which is not the same as this element. Okay, so we are abstracting this out. Okay, so it makes your head hurt. Okay, so D1 is EE prime. Can we have EE and EE also? There are too many E's here. Can one transaction NQ element E and another transaction NQ the same element E? Remember, each element has a unique ID. Okay, and actually that ID is assigned when the element is entered into the queue. Okay, so it's not like Java object hash code actually. It really means that we do want to separate all the objects in the queue at one time. Okay, so that condition can never occur, that two different objects will have different IDs. In fact, okay? You can't have the same object be NQ'd twice because they're two different objects, and so that's not possible. EE DE prime means transaction 1 NQ'd E and transaction 2 DQ'd E prime. Can we have EE and DE also? transaction 1 enqueued E and transaction 2 is dequeuing E?
But the DQ is dequeuing an element that existed. That's not the one that just got enqueued.
No, so this one means it's not the element that got enqueued.
Yeah.
If I have EEDE, that means a later operation dequeued an element that the previous operation enqueued. Can that happen? Yeah. Right? You enqueue some element, it got dequeued. Can you have the reverse way, DEEE? The first operation dequeued an element and the later operation enqueued it?
You said these IDs are created when they're added to the queue.
Yeah.
Right?
Right.
So then no.
No, you can't have that situation. Okay? Okay. You can have some DEEE prime, but you can't have DEEE. Okay? And you can have DE prime. Okay? One. Can you have DE? Okay, just as you couldn't have EE, you couldn't have DE. Okay? So now we have to go and figure out which of these relationships do we consider for serializability? Okay? Which of them create dependencies? So, which of them are not commuting? So, which of these commute? Does this commute? No, I mean, if you know this, if they come in different order, then it's not the same. But different transactions will get different values, right? So this one, does it matter in which order it got done? No, it doesn't matter, right? Because you got a different element. This one matters. This one doesn't matter. This one matters. Okay? So our cycles in D1, union D3, union D5. D2 and D4 don't matter. Okay? They are like the read operations before. Even though they involve writing. Okay? They're working at different ends, so they're fine. Okay? So to avoid cascaded aborts, what relationship should we prevent? Where is there some leakage of information? If I enqueued E and you enqueued E prime, if I abort, should I abort you? No, what I did was not even visible to you. In this case, no. This one, yes. No, no, right? No D3 relationship in concurrent transactions. Okay, that's like the read-write dependency we saw earlier. Okay. Questions? Okay, so we have now EE, DE, and D null. Okay, and null represents the case when the queue has no element in it, right? And let's put the pointer on again. So EE and EE not applicable, EE, DE not applicable, because if you've dequeued E, EE can't come later. And let's reason this out. If somebody else found the queue null and they got a lock for it, and you try to enqueue an element, okay, you should conflict because they might not have got the null value if you had enqueued your value successfully. Okay, so they don't commute, basically. Right? So I guess we'll come to that later. No, yes, you can't have, these don't commute. This commutes. No, not applicable. DE couldn't have come first. These two commute, and they don't. And we have a separate entry for null because we don't want null to be E prime. Two nulls are different, right? So don't commute. Don't commute. If somebody else got E and you got null, if you were reversed, you might have got E. Okay. Don't commute. So this is, hang on, this is D null. D null comes twice? Sorry, this is, okay, sorry. Okay, I'm getting confused. So this is again D null and EE, and don't commute. Same thing as E prime, doesn't matter whether it's E or E prime. No, again, E prime don't matter because they're not null. And finally commutes, right? So we allow this to happen. So firstly, I sent a message to you guys on Piazza right after class. I thought I'd found a situation, and I went off to lunch, and then I looked at it again at around 8 o'clock and said, "Oh, that doesn't work." And I convinced myself that two-phase locking really does protect you, and you won't get into trouble. Okay, if you guys can come up with another example, that'd be good. But even though you have to remember what elements got NQ'd and DQ'd, it seems it'll work. Okay. However, I started looking also at this this matrix that we've filled in class, and I had issues with it. Okay, so let's just look, and all the issues came arose because of this column and this row. Okay, so what did we say? We went and did the regular part, okay, which is the one that I took from a paper, and then we did the null part, okay, and so we filled all no entries except for one, okay. We filled here yes, saying 2 D nulls commute, so we allow that to happen. Everything else we say yeah. Again at this, and by the way, this D null stuff makes sense only if we assume the DQ is non-blocking. Okay, if this Q is like a bounded buffer, and if you guys remember your bounded buffer, a DQ operation on an empty buffer will do what? So if the buffer is empty, it'll.
Is it blocking?
So if it blocks, it'll block till the buffer is non-empty. Okay. So this null thing, I think they didn't consider in that paper just because they were assuming the regular Q. Okay. We complicated things to make that case fail, and now that we've complicated things, let's try to really understand it. Okay. So we assume DQ is non-blocking, and we of course again let's just go through this. Now let's look at EE and D null. What does it really mean? It means somebody NQ'd an element E and got a lock on that. And somebody else is coming later and finding the Q to be empty. So do these operations commute? Are they, what's going on here really?
Well, one thread could, so the Q is empty.
Right.
One thread comes along, obtains the lock to NQ,
yes,
but hasn't actually NQ'd yet.
In that case, okay, and I'm trying to get the lock. So you're saying that, and you're saying that should fail. So maybe you are, okay.
Yes, it should still fail.
So it's NQ'd the element, but hasn't really NQ'd. It's trying to NQ, but hasn't really NQ'd, you're saying. Yeah, I hadn't thought of that. I thought maybe this is not applicable. And then if we allow this guy, if we give him the lock, what bad things are going to happen? He's going to find it null, and then it's not going to be serializable. Okay. So I was going to say that allow it to happen, and later, so I didn't think of the situation where this guy's NQ'd it and hasn't got the lock and hasn't really NQ'd it. I didn't think of that situation. In which case, I said, okay, the only reason he'd find it null is if this transaction itself went and DQ'd the element later. Okay? And if it DQ'd the element later, let that find the problem. Okay? So, but then I think the previous slide would actually work fine. Let's see some other cases. D null. So this guy has done null, and he's found it null, and he wants an element, so that should be no. What does this mean? This transaction found it null, and this transaction is trying to enqueue an element. Sorry, he's trying to dequeue an element. Okay, so the same transaction could have done an enqueue, in which case this guy can go and conflict with that later. So we can either say not applicable. We can just go and say yes at this point, saying nothing bad's happening here. Okay, and let something else figure that out. Figure whether that operation should be allowed or not. We can say no at this point and say, look, some other transaction may not enqueue, and maybe this transaction is enqueued, in which case it won't conflict. So I mean, it gets complicated. So basically, because we have to think further. If we say no here, we are trying to anticipate what other operations might occur later. But for now, there seems to be nothing wrong with allowing this guy to enqueue, or with dequeue, because some other operation must have happened, and let that operation decide. Guys buy that? Okay. So at least the thinking we're doing here, and DE and DE prime don't make a difference relative to null, so this becomes yes, of course. So maybe I will go back to no here, because Nick is right. It might have got the lock and not actually exercised the operation. I didn't think of that situation, in which case I was saying yes here too, just as I was saying yes here. Okay? Question?
So for DE and D null,
Yeah.
you're saying that just because there's a D null lock, we should still be able to require a DE lock because something else could have added it.
And that's something else that would have added, yes, would have tried to get some kind of lock. And if that lock conflicts with DE, DE will find that invalid, will not be able to get the lock.
Okay,
and if something else doesn't conflict for some reason, we don't have to think further.
Right.
I'm just saying, let's not, rack our brains and try to figure out whether this E was put by this transaction or by another transaction or by some non-conflicting transaction. Let's just say yes at this point.
Yeah, I was going to say there's no way for that transaction to be added while a D null lock is had. That doesn't matter, because we're saying in that case the conflict's going to pop up somewhere else.
That's what I'm saying.
Okay.
And I was making the same logic here too, but I didn't think of the situation that there might be a slip between when you ask for the lock and actually you make the operation. Okay. So we'll go back to no here. Okay. Fine. Okay. Okay. So type-specific locks. The main point is that less information about operations available to locking, more conservative it is about commuting and dependent operations. Okay? So the more the transaction system knows about the operations, the more liberal it can be. Okay? And no information means serializability. No information. Under no information, serializability means no interleaving concurrent operations on an object. And cascaded abort means no concurrency. Okay? So interleaving means that as long as my operations follow your operations, that's fine. But if my operation came after your operation and you had an operation that came after me, then we can't, that's not allowed. Okay? On the same object. Read-write serializability, no cycles in these three relationships, no cascaded aborts, no DWR relationship. And Q-specific, we take these relationships. Cascaded aborts, we don't allow a DEE relationship. And in this case, a lock specifies kind of operation and element queued or dequeued. And they kept on until the end of transaction, and we'll try to figure that out And in general, what we've done in this slide deck, or in this whole big concurrency control lecture, is asset properties and transactions. We looked at the idea of isolation. We focused on the I. We looked at explicit and implicit locks. In your implementation, some of you have done implicit locks. Did I require implicit locks? Oh yeah, but some of you also done preemptive locks. Okay. We looked at distributed locking implementation. Two-phase commit was an alternative, and we have replicated systems. We didn't really look at how two-phase commit works, but we said that look, if we have totally replicated lock histories, then that's what would be useful. Whatever that algorithm is, as it implies, there's multiple phases of agreement. And in the centralized algorithm, we looked at cache incoherence problems and how to solve them, at least for the particular case that we are dealing with. We looked at shared versus exclusive locks. We looked at two-phase locking, okay, hierarchical locking and intention locks. We just looked at type-specific dependencies and locking. And then we looked at optimistic transactions. Optimistic transactions are a contrast to pessimistic transactions where we have locking. And then we can have something in between, which is optimistic locking. Okay, we saw what that meant. We undo the operations once we know whether we have the lock or not. We'll nested transactions. Okay.